Hola, chaps. Let's learn. Hola, chaps. Once upon a time, there was a little boy, and this was, I think, in England and was in the 1700s or so. And the way they did things back then was if you wanted toast, you would take some bread and cut it up. They didn't have sliced bread back then. And you'd skewer it and then hold it over the fireplace flame to heat it up and make it into toast. So he made toast one morning, and his mom had also baked an apple pie. And when the pie came out of the oven, it was very hot and, smelled delicious. And so the little boy cut himself a little piece of apple pie and took a bite of it and realized, wow, that is really hot. And on the other hand, when he took a bite of the toast coming right out of the fireplace, it wasn't hot at all to him. And so, with his burned tongue, he asked his mom, Mom, why is the apple pie hot when I bite it, but not the toast? Do you know what she said? That's right. She said, I don't know. Turns out no one in the entire history of the human race had actually ever noticed that hot apple pie can burn your tongue, but hot toast doesn't, even though they're technically at the same temperature to start off with. And so that led to the study of specific heats of materials, as we call it today in this chemistry unit. So it all started when people, the boy, actually realized that different substances hold heat differently, and apples hold heat much, much better than bread. The reason for that, I can tell you today, is because, well, the apples have a lot of water in them. The bread does not. And water is an excellent substance for holding heat. Our oceans do a major effect on the weather and climate on this planet because of their heat capacity compared to rocks and the solid part of the surface of this planet. So I went and I fished up three different substances. I have here a copper block, a steel block, and an aluminum block. Now, at one point, I thought I had a lead block. Apparently, I didn't bring it home, but I did bring home a iron block. And so, for me to do some demonstrations for you, the first question I have for myself is, well, is the iron block the same thing as the steel block? Because my understanding is that steel is essentially iron with just a little bit of other stuff added to it. So it's not pure iron, but it's pretty close to pure iron. So the first thing I want to establish is, well, does this iron block and the steel block have the same density? If they do, then I would say, well, okay, iron and steel are close enough to each other that I can use these two for as being this different sizes of the same substance if I want to do a demonstration with that. So how do I establish if they have the same density? This is a review question that all of you should be eager to answer. So this is called a dial caliper, and you use it by first making the two arms go to zero. I guess I can show you this way. The two arms go to zero and verify that the scale, the dial, is reading zero. And then as you open it up, you split it apart. You put the part in here that you want to measure, like my finger. And on the dial, you can read, when I zoom in, you can read in units of inches, in this case, how much of an inch it is. So the way the dial goes, that is zero. This is 10/100ths of an inch. Here would be half an inch on the dial. This would be 0.75 inches, zero point 0.8, zero point 0.9. And so one complete revolution of this dial corresponds to 1 inch. Okay, so 0.1, 0.5, 0.75, 1 revolution is 1 inch. And I'm going to measure the dimension of the steel block. It is identical to the other two blocks. And I guess I could do the dial this way, and you could observe that as I open it up and place it over this part and close it, it closes down to exactly 1 revolution. So these cubes, the small ones, each are 1 inch on a side. The larger cube is more than 1 inch. So starting at 1 inch, I open up the dial calipers and I bring it over the part and I close it down. And even you can see, although it's not zoomed in, that that is a quarter of a circle. So I'm declaring this to be 1.25 inches on each side of this cube. And if I did zoom in, you'd be able to see it better, but okay, you trust me. Next, what is the relationship between the mass of this cube and the mass of that cube? So I brought in the kitchen scale and let's mass the two substances. I'm going to put this to where you can see the reading this time. So the top camera lets you see the image on the display, and the side laptop camera lets you see. Yes, I'm putting this on to the scale. All right. So for the small steel block first, when I put it on, I see it has a reading of 130 grams. When I put the larger iron block on, I see it has a reading of 247 grams. All right, you now have enough information that you could calculate the densities of these two blocks and compare them and see, are they really close enough to being the same substance? Close enough meaning, well, let's say within 3% to 5% at most. Do they have the same density? No doubt you recall that the formula for the density of a substance is density is equal to mass divided by volume. Now, the volume in this case was in units of inches, but if I want to compare density on Lord Google or something, I would, for myself, prefer to work in metric units. So I would take the English measurements of the dimensions of the cube, and there's my crude drawing of the cube, and say each side was either 1 inch or 1.25 inches. So 1 inch, as a reminder, you probably should have memorized this, is equal to 2.54 centimeters. So the thing to do now is to calculate what is the volume of 1 cubic inch in centimeters. And if you say 2.54, you're wrong because each of the three dimensions is 1 inch, length times width times height. So it's 2.54 times 2.54 times 2.54 or 2.54 cubed. Beep, beep, beep. So 1 cubic inch is equivalent, my calculator says, to 16.4 cubic centimeters. All right. What about the other cube, the one where each dimension is 1.25 inches? Is that just 25% greater than this? No, 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 no. Because each of the three dimensions is 25% greater. So it's much easier if I just go 1.25 inches times 2.54 centimeters, enter, and it says 3.175, and I now take that result, so 1.25 inches converted to centimeters, and I cube it, enter. So for this larger cube, the volume is 32.0 cubic centimeters. And by now, you've paused this and you leapt ahead of me and you calculated the density of the two substances. Well, the two different cubes. So for the small cube, the steel one, the mass was 130 grams and the volume was 16.4 cubic centimeters. 130 divided by 16.4 is 7.93 grams. And I could write per cubic centimeter, but a cubic centimeter is the same thing as a milliliter. So I'm just choosing to write it as 7.93 grams per milliliter. Then for the large iron cube, its mass was 247 grams. Its volume was 32.0 milliliters or cubic centimeters. So 247 divided by 32, and I get 7.72 grams per milliliter. So looks pretty close to me. If I wanted to get technical and measure what is the difference between them as a percent, I remind you, experimental minus accepted divided by accepted times 100% is your percent error. So if we say that the iron block is the accepted value, well, okay, it's not going to matter significantly which one I call, but let's do it. So, 0.72 minus 0.93 is negative 0.21. The sevens, I didn't bother doing them. I'm going to divide that by 7.72 and then multiply that by 100%. And I see that my error is less than 3% difference between the two of them. And maybe that's because steel just has a little bit of impurities in it compared to iron. But I'm going to declare that this shiny steel block is the same substance as this much duller looking iron block. Okay, so I have these two cubes, 1 inch cube of steel, 1 1/4 inch cube of iron, and to within 3%, they have the same density. So what am I going to be doing? What I want to do is to heat these substances in a beaker of water, and actually I could put it into a pot of water. I tried to establish with you that water on a heating curve rises up. If you looked at the video of me melting ice, heating ice, it had some funny stuff at the beginning, but at the end, liquid water heated up, and when it got to about 100 degrees, it plateaued. And no matter how much longer I boil the water, it's not going to go hotter than about 100 degrees C. So, what if I took a container of water and I put these different cubes into that container of water? Which one would become hotter? They would all eventually come up to the same temperature as the water that they're in. So if I put these three cubes into a container of water on a hot plate and I heat it up till it's boiling water, then each one of these three cubes should be at a temperature of about 100 degrees Celsius. And I want to start with that, having all three of these at the same initial temperature that is above ambient temperature. And my plan right now is to take each of these three cubes one at a time, because I only brought home one calorimeter and da 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 da. So one at a time, pull these cubes out of the boiling water, not with my hands, and quickly dunk it into a calorimeter. The plan is to dunk these one at a time into a calorimeter. Here's one. If you missed the previous episode, this is just a very simple thermos container, a cheap one, if you want to put it that way. And it's just a metal container inside a metal container with a little ring trying to keep it from transferring heat very quickly. It's got sort of a rubber type or plastic lid on it. It's got a little steering rod that you can use to make things agitated. Not really necessary for this experiment, but here's the equipment. And what I would do is use a graduated cylinder and carefully measure out some quantity of water, maybe 100, 125, 150 milliliters, something that won't spill. Put it into the calorimeter, have all the water coming from the same source all the time. So have like a pitcher of water, and all the water that comes from it is always, ambient temperature. Measure the same quantity of water, put the water in the calorimeter, measure its initial temperature, pull 1 cube out of the boiling water and dunk it into the calorimeter. Have Logger Pro record the temperature maybe every 6 seconds, maybe more frequently, and make a graph of it until it kind of reaches equilibrium. So what's going to happen is the heat lost by the hot material cooling down is going to be equal to the heat gained by the colder water warming up. And they will meet not in the middle in terms of the temperature, but in the middle in terms of heat lost versus heat gained. And that's something that is a formula for us to calculate. So I want to do that for 1 cube and then dump out the water, pull the cube out, measure off the same quantity of water again, put it in the calorimeter, get Logger Pro ready to collect more data, pull the second cube out of the boiling water, try to drop it in without splashing any water out, have Logger Pro record the temperature as a function of time, making a second plot, ideally a second plot on the same graph. I think it can do that. Once it, reaches equilibrium, dump it out, repeat the process a third time with the third cube, and each time having a new plot being added as an overlay on the temperature versus time graph. What happens when you put three identically sized substances made of different materials into the same quantity of water that's at the same initial temperature in a calorimeter? And so all of this is sort of like an intention to be an introduction to this part of the reference sheet. Haha, your handy dandy physics and chemistry reference sheet from June 5th, 2019, page 2, that talks about the specific heat of these different solids. So the solids that I picked are on this list: aluminum, copper, and iron. No, I don't have any zinc. No, I don't have any gold, which isn't on the list either. So really the next step is to go outside and then start conducting these experiments. All right. Here I've taken the data that was collected by Logger Pro for each of the 3 cubes, and I've put it together into a single Google Sheets chart. So here's the information in words saying the blue line, when you see it, represents the aluminum cube. The red one is copper. The yellow one represents iron. This was where each of the 3 cubes was initially at a temperature of 100 degrees C or 99 degrees C in boiling water. Then one at a time, they went into a calorimeter, each time with 150 milliliters of ambient temperature water. I used a Logger Pro probe to record the temperature once per second for 5 minutes. And here's a graph of the results. Again, the blue line represents the aluminum, the red line represents copper, and the yellow line represents iron. And as I put in the written notes, I believe that spike early in the curve, the yellow curve representing iron, is an artifact of the temperature probe directly touching the iron cube inside the calorimeter before it had time to transfer its heat energy to the water surrounding it. So, as far as data analysis goes, I would ignore that spike. What's more relevant is what is the equilibrium temperature reached by each of these three cubes before the entire calorimeter started to cool down. So you're looking for the peak in the region of the curve where it is gradually changing. Somewhere between 3 and 4 minutes is typically the data point I would use. Ciao.